start with, we'll have Professor Zhu from the Department of Chemical and Biomedical Engineering at the University of Akron. He's going to talk about quantitative thermal conductivity analysis with scanning thermal microscopy. So, Professor Zhu.
Thank you very much.
I think this is good enough.
Oh, this is?
So you don't have to hold this. There you go. All right, thank you.
This is all right?
Oh, you want a microphone?
Okay, I think this is better.
Okay.
Anyway. Okay, good afternoon, everyone. I hope you enjoy your lunch. And welcome back. Thank you very much for the great opportunity to be invited to enjoy this exciting symposium. I missed my connecting flight last night, so missed the earliest flight to be here is 9:30 in the morning to be in Albany. So I missed the first two talks. I really want to learn from those talks. So hopefully we can still discuss something after this presentation. So by the way, I'm Jiahua Zhu from the University of Akron. Today, I'm going to talk about a little bit different topic on the scanning thermal microscopy. In this morning, I learned a lot from other techniques, from other professors and the industry, a lot of work experience in this area. So why we're interested in this scanning thermal microscopy? Because personally, I'm interested in thermally conductive materials. Right now, you can imagine for those electronic devices, like heat accumulation, heat dissipation could be one challenge, especially the dimension of those devices become smaller and smaller. So we talked about 14 nanometer, 7 nanometer this morning, and then when you go down that kind of scale, the heat accumulation of those small devices could be a huge problem. So heat dissipation from those microelectronic devices, even LEDs or even aerospace, a lot of big structures, the heat accumulation is a huge problem. So that's why we're interested in this kind of technology, how to mapping out the thermal conduction property of materials at nanoscale. So if you don't know Akron, we're just very close to Cleveland, Case Western. we're very close. So Akron actually is called a rubber city. The Goodyear, Bridgestone are all based in Akron. And if you know LeBron James, Akron is his hometown. He left already, right? Yeah. And also the Quaker, also based in Akron. We have very beautiful national park. This national park, I don't think there's very special thing in this national park. Very good area of forest and a lot of state parks. And this coming month, October, November, is going to be very, very beautiful. So if you get a chance to visit Akron, stop by, say hi. Okay. So I'll give you a brief introduction about why we're interested in this technology and what is scanning thermal microscope. And scanning thermal microscope can be used for composites. Now, composites is the major material used for thermal conductive applications right now, and there's a lot of understanding has not been yet understood yet. And we are going to use scanning thermal microscope to develop a model, and trying to develop quantitative measurement technologies. I will give you a reason why we're interested in this kind of model work. In terms of the application of the thermally conductive materials, you can imagine, like, for example, LED, the light. If it's a high temperature for LED, the lifetime will be much shorter. And for PCs, okay, the CPU generates a lot of heat. Normally, you apply called a thermal paste. A thermal paste with certain thermal conductivity that is able to transport heat out of the CPU to the environment. And then you apply fans to get all those heat away. But those kind of materials, for example, the modeling, the most advanced composites right now, materials right now for thermal kind of applications, composites. Now, if you can imagine now, composites for thermal conductivity and electroconductivity are two totally different concepts. When we talk about electroconductivity, we typically use electrical percolation. So above certain weight percentage of electroconductive fillers, you will see a dramatic jump of the electroconductivity. And that percentage, we call it percolation. But thermal conductive materials, there's no percolation you can find. It's just a gradual increase of thermal conductivity. And that relies on very, very large of thermal conductive fillers. And in that case, people consider that for composites, the major thermal barrier is from the polymer or under the filler interface. And that interface, why it comes with high thermal resistance, and how to minimize the thermal resistance to make the composites more electrically conductive. This area has not been developed yet. And at the interface, you can imagine, polymer and the filler interface, typically we're talking about a few nanometers. We call it nano confinement, for example. That a few nanometers, and the existing technologies for thermal conductivity measurement, we're not able to selectively detect the thermal conduction at a very small area like that. And that scanning thermal microscope becomes a unique tool to detect what kind of properties we can get at the interface, or we can get from polymer to filler, and in between the interface, get across what kind of property we can get across the interface. And if we can get good property on the interface, we can typically generate a good understanding about how the heat transport and how the interface play the role in thermal conduction. And this is the major background and why we're interested in this kind of research. Now, this is the composite, typical composites. Now, if we talk about the highly crystalline materials like the diamond or graphene or carbon nanotube, it comes with very high thermal conductivity. The reason is that these kind of materials are highly crystalline materials. Now, with those very strong covalent bond between the atoms, this thermal conduction is just like a spring mass system, comes with a very ordered structure. So the phonon propagation along the lattice structure is very fast. So the heat transport relies on phonon scattering, phonon propagation. If we have a very good structure like this, if it's very good, and then the phonon can be driven through along the crystal structure, and then you can get a very high thermal conductivity. But when you have this kind of composites, say left side is crystalline structure, right side is polymer. Now, crystalline materials, typically inorganic, like boron nitride, carbon nanotube, diamond, graphene. Those kind of materials have different phonon frequency or vibration frequency, we could say. With polymer, because there are two distinct materials, it comes with different vibration frequency when it's exposed to phonon vibration. So at the interface, the mismatch of the vibration frequency of the two materials generate a lot of phonon scattering at the interface. And that phonon scattering will prevent a good thermal transport across the interface. That's a general understanding. But what we find is maybe it's not true. Maybe the polymer surrounding those nanostructures has different behavior. For example, the crystallization, crystallinity will be different surrounding those nanostructures, and how that spatial phenomena, interfacial phenomena, will affect the thermal transport across the interface. That will be able to help us to generate some new understandings about the composites. So the two main questions we have here is how the interface affects the thermal transport in composites. This is very important to improve the overall thermal conductivity of the composites. And the other one is, once you have some information from SThM, now the existing technology for SThM, we can basically compare, relatively compare, which area is high thermal conductivity, which area is lower thermal conductivity, but there's no way we can quantify the thermal conductivity. So we have to find a way or build up a model to construct the thermal conductivity model that is able to tell the absolute thermal conductivity based on scanning thermal microscope. With these two questions answered, we should be able to know which area has higher absolute thermal conductivity value, which area has lower. So the existing technologies, basically to measure the thermal conductivity, there are steady state method and the non-steady state method. Now steady state method, of course, you measure the temperature versus T time. As long as this temperature versus T does not change, you can, for example, on the sample, you build up a lot of thermocouples to measure the temperature gradient on the sample and then build up the use Fourier's law to calculate the thermal conductivity. And for the transient methods, for example, the transient plane source method and the laser flash or the D-link method, all these methods, you don't need to reach equilibrium. You can make the measurement very quickly, but to get reliable thermal conductivity values, you need a lot of data analysis. So both methods has certain advantages and disadvantages. Now, if you compare different technologies in terms of spatial resolution, temperature resolution, and the response time, the uniqueness of scanning thermal microscope is that the very small spatial resolution, which is in order of 0.1 micrometer. So this is the unique why we are interested in this technology, because we want to study the interface. The interface is around a few nanometers to sub-micrometers. And only this technology can be used to tell the difference of interface in composites. So in terms of the working principle of the scanning microscope, as we know, this is built on the FM, and we bought a system from Parker, and then we use a scanning thermal microscope. This is the thermal probe. The uniqueness of this thermal probe is the thermal probe can be heated based on the connection with the Wheaton bridge. Now, once your sample is heated to a certain temperature, and you use that tip to scan across the sample surface, if the sample surface with different materials, of course, it comes with different thermal conductivity. From polymer, matrix to filler, you scan through. Those different materials have different thermal conductivity, and if that area comes with higher thermal conductivity, more heat can be propagated through the sample, and your tip surface temperature will be decreased. And to make sure the constant temperature of the thermal probe, you need to apply a current to compensate the heat loss through that heat transport process. So that means if you get a higher compensation current through the Wheaton bridge, that spatial area comes with higher thermal conductivity. So by scanning through all the samples at a scan area, you can point by point to get the different thermal conduction. I cannot say thermal conduction value, but relatively thermal heat, which area passes more heat, and which area comes with relatively higher thermal conductivity. Okay, so we want to understand the role of composites interface structure in thermal conduction by experiment. We can do that. The other one is we want to quantitatively measure the thermal conductivity by SThM. Now, this is not only experimental can do that, and also requires a modeling, and I will tell you why. First of all, we make a very simple composites. We use PVA and magnetic nanoparticles. The reason we choose magnetic nanoparticles because we want to use magnetic field to get some alignment of those nanoparticles. As you can tell, now as we apply the magnetic field, you see those lines of the magnetic particles, and then based on that, we can get a few different patterns. From bulk measurement with pure polymer and polymer plus magnetic nanoparticles and polymer plus magnetic particles applied by magnetic field, we get increased thermal conductivity with these three samples. And then we use microscopic use scanning thermal microscope to get the probe current. And you can see the clear trend. The trend is follow the same pattern. That means the bulk measurement of the thermal conductivity is consistent with the macro measurement. Now, this consistency can tell us we can use the probe current to reflect the thermal conductivity of the materials, and this result is consistent with bulk measurement. So we have to make sure the first thing. And then we choose particle aggregates. Okay, from the left side, we pick up 5 points. From the right side, we pick another 5 points. Now, those 5 points are taken from sample to interface, either left side and right side. On the right side, you can tell the thermal mapping of this sample surface. We do the FT curve to get the stiffness of all those data points we marked on this figure. And we start to measure the probe current at those areas. And you can see the clear trend of the stiffness and the probe current. Interface, it comes with a different property of bulk polymer. The polymer at interface, due to the nano-confined effect, the crystallization behavior could be different. And if it gets better crystallized, it comes with larger stiffness values. So you can tell if you get more away from the particle surface interface, and then you get smaller stiffness. Smaller stiffness, you also get smaller probe current. So it seems like stiffness has certain relationship with the probe current, and the stiffness is positively proportional to the thermal conductivity. And again, we take another two particles as an example. For example, this small and the large particle. I take 7 different points, and we do the analysis on those points. If you take a horizontal a comparison, like data points 475, data points 263, all those from bulk polymer to interface to particle surface, okay? And then we can find out, okay, it's a clear trend, stiffness decrease, probe current decrease, stiffness goes up away from the sample particle surface, and then the probe current goes up again. So all these trend clearly tells us the interface surrounding those particles or particle aggregates give you different stiffness value. The more close to the interface, higher stiffness you can get, and the high probe current you can get out of those areas. And if you get magnetic alignment, say we have 2 particle chains, and then what we can observe between the particle chains. This is something different we observed. If you got 2 particle chains, the interface between the particle chains, it seems more likely to confined and get more crystallized. So the interface area in between, you get, for example, this is this is a particle surface, get along to the both sides, you get a larger stiffness and a larger probe current. So out of this work, what we conclude here is traditional composites believe that the interface is the thermal barrier, and that it will restrict the phonon propagation across the interface. But if you have nanoparticles in the composites, those polymers surrounding those nanoparticles, it gets different crystallization behavior, and the stiffness is increased. Those area could be a thermal conduction area instead of the thermal resistant area. And from this work, we also find that traditional study tells us, for example, the nano-confined area is in nanometer range. People always believe that. And that could be true in terms of physical phenomena, but in this phonon propagation across the interface, this interface area can extend to micrometers instead of nanometers. So this is a new understanding about the interface phenomena, about the thermal conduction. So far, what we get is, okay, we can build up a correlation between the stiffness and probe current. But that probe current does not give you absolute thermal conductivity values. How can we use this kind of mapping of probe current to get absolute thermal conductivity from different areas? So this is the major challenge, because you can imagine when the tip get in contact with surface, the surface is not smooth. And that non-uniform surface give you different contacting condition at every single location. And how can we get quantified results? There's basically no way we can do that. And also, if the sample surface comes with different hardness, you apply the same force of the probe, the contacting area of your tip and the sample surface could be different. So we want to use a model that constitutes all those parameters we can think of from the contacting of the tip and the sample to get a generalized model to describe the contact resistance between the tip and the sample surface. Now, we need to consider the entire heat flow from the tip to sample surface. If you do the heat balance or heat transport analysis from the tip to sample surface, you can consider 2 parts. Now, the tip is the heat generator. It comes with a certain heat flow from the tip. And then between the tip and the sample, there's air gap or whatever, the small contacts. That part gives you a certain heat resistance. And that will consume certain part of the heat flow. And part of the heat can get over that interface and transport it to your sample. So the total heat will be equal to the heat goes to the sample plus the heat is consumed at the interface. So this is the general term we can consider for the entire heat flow. Now, in this case, the challenge is the thermal contact resistance varies with measurement, because the surface can never be uniform at nanoscale level. And the TCR is related to many factors. This contact resistance depends on the roughness, hardness, a lot of factors in this experiment. Now, the first thing we can think of, or we want to solve this problem, is how can we model this interface between the tip and the sample? The resistance, how big, how small the resistance is. So in this model, what we want to introduce is the probe current is something you can read from your SThM. That's something reading out of the instrument. Surface roughness, micro hardness, surface probe, slope. That's 3 other parameters we can consider from the sample surface. And we can do those analysis, roughness, right, hardness, all can get from the readings. And also, we have loading force that can be adjusted from the instrument. Tip radius, of course, it depends on which kind of tip you can use, and other equipment constants. So you can imagine there are a lot of other parameters you need to consider to make sure you get a reliable model. And after that, we still want to use the microscope measurement to make sure, okay, whatever the model you developed, you get certain results. Is that matched with the bulk property? Because the small scale measurement sometimes is not consistent with bulk measurement. So we have to use bulk measurement to back calibrate the model we develop to make sure our model can describe the bulk properties, even if from a microscopic model. Now the TCR, thermal contact resistance, how we model it? We can simply divide the heat flow into the heat spread on the macro contact level, and at the macro contact level, we consider the heat flux. So the total sample surface, the total contact resistance, we can write into the summation of the macro contact resistance and the micro contact resistance. And these 2 terms of the resistance can be further write into those 2 terms after this formula. Of course, we use a lot of principal series to derive this formula. And in this formula, the K is the sample conductivity of your sample. A is the tip radius. Now this is defined. Once you choose the tip, you have defined the radius of the tip. And the K I mentioned already. H is the hardness. Sigma is the roughness. F is applied force. M is the slope. Now the slope is important. That describes when your tip get in contact with your sample, what's the angle of your sample surface? Because that matters. So once we get a TCR, and then you need to put everything into the heat transport analysis. So the energy balance, Q total, will be equal to QR plus QF. We mentioned that already. And from Fourier's law, say QR equal to delta T over the divided by the R system. So this is the general term to get the resistance. So by using the moving heat method, we can describe the sample resistance in terms of the R0, which is the sample radius, the tip radius again, and K, the conductivity of the sample. So eventually, once we write everything into this formula, and then we replace the QR contact with the formula we divided from previous slide, we can write into that formula that describes the relationship between probe current and all other parameters. And all other parameters is something we can either read or analyze from the scanning thermal microscope testing results, or that is something we use as a parameter for the input during the measurement. So everything can be measured. Eventually, what you get here is a relationship between I and all those parameters, right? So once we get here, and then we can simply do some testing, or we think of, is there any way we can make this model simpler? So we did 2 polymer testing. We chose 2 polymers, like a PDMS with 20%. Now 20% is the curing agent. percentage during the mixing process. And the 30% epoxy is 30% curing agent as well. So we use two pure polymers. At this stage, it's still too complicated to use composites. Because when you deal with composites, the particle area and the polymer area comes with totally different properties. So it's very difficult to get all the information. So we choose pure polymer, and we get all those parameters. We got probe current, surface slope, surface roughness, and the thermal mapping. Now, once we get here, we can use all those results to verify, okay, which model I can use for certain materials. For example, the PDMS system. The PDMS system, if you can get all the previous results and we calculate RMA and RMI, the RMA is much larger than RMI. So in that model, we can basically ignore the RMI, and it becomes a relationship of I current, and this term can be eliminated. For epoxy system, it comes with larger roughness, and then those two terms are at the same order of magnitude, like powers of 7. So we cannot eliminate any one of them. So these two different models developed for two different materials is only because these two samples come with different roughness. So that means roughness affects the thermal conduction a lot. Okay, once we get there, okay, we got a PDM system with different percentage of curing agent, and we can develop basically the same material but the different properties. So we get all those measurements like the thermal conductivity, probe current, hardness, roughness, probe current, and the revised probe current versus thermal conductivity. And eventually what we get here is, by using the model, we get a very good correlation between the revised probe current and the thermal conductivity. This is a linear relationship. And what that tells us, I will give you later. Again, use the epoxy system. Epoxy system, we do the same measurements for all those properties. And then what is important here is, instead of the linear pattern of revised probe current versus thermal conductivity, we get a nonlinear pattern for epoxy system. And that makes sense. To further verify these models, now we can control one more parameter, which is the applied force. Now, in this linear pattern, for example, PDMS system, because that term is eliminated, so the force is not involved, the applied force is not involved in this model. So if you apply the different force, supposedly we are not going to get any change of the results. And actually, this tells you that we apply 3 different forces, and we get pretty much the same results. But on the right side, the nonlinear pattern, because this model is force related. If you increase the force, the I will be increased, right? So if you can tell from 3 different sets of the force values, you increase it, you get higher probe current results. So based on these linear and the nonlinear models, why this is important? Y-axis is the revised probe current, x-axis is the thermal conductivity. So that relationship means if we can get a reading of the probe current, we can project or we can predict the thermal conductivity, absolute thermal conductivity of your samples. Okay. And then once we develop those models, we want to verify our model, so we choose a different material system. We use PDMS and epoxy to build up the model, and we use PVA and PVA with metal ions to test our model. And these materials, again, you see, we perform the measurement to get all those parameters. And the thermal conductivity is here, probe current. It follows certain trend, but it does not necessarily help us to get a certain relationship. So all these red points are used for development model. And if you extrapolate this line, linear model, you can get this dashed line. Okay. Now all those blue dots are experimental results, and these crosses are model results. So you can tell, even though we measure a small range of the thermal conductivity value, or we build up a model based on all these data points, you extrapolate this model, you can get pretty much good prediction results. So this model is kind of solid to predict semiconductivity of polymer-based materials only at this moment. So we want to see, okay, how it works for composites in the future. And out of these models, like, we get basically two models, linear model and the nonlinear model. In the linear model, your probe current is follow the linear pattern with the semiconductivity value K. And in the nonlinear model, it does not follow a linear pattern, of course. And the factors in these two models, why some models are linear and why some models are not linear, is only because the roughness of the samples. If you get small roughness, and then your probe current is force independent, so you can get a linear curve. And if you get a rough sample surface, the contact on the rough surface is more sensitive to the force applied to the sample surface. I think that is generally easy to understand. If it's relatively smooth, you apply larger force, contact area does not change too much. But if that is a surface with larger roughness, you apply larger force, basically you can find some gap to fill in and get larger contact area, and that will affect your reading by applying different forces. So come to the conclusion. SThM provides a unique capability to measure heat transfer at micro domains down to 0.1 micrometer. So this is a special feature of scanning thermal microscope. And we generate new understanding of composite interface. And actually, this is the positive relationship between stiffness and the probe current. Model development for quantitative thermal conductivity measurement with SThM. I think this model is very useful, and that enables us to measure thermal conductivity down to 0.1 micrometer. So this is a unique feature we developed from this. And right now, we found out that the surface roughness actually great influence the quantitative model, but it might be some other factors. For example, the hardness we found. Hardness, the same thing. Like if your material has a large, higher hardness, then the contact area is not going to change much if you apply much force. And then if it's a very soft surface, you apply large force. Basically, you can change the contact area, and then that will generate different heat transport phenomena from probe to sample surface. There's much more to be explored. That's what I want to conclude. And then this actually, to develop the thermal model, it involves a lot of efforts from my student Ivan. And even though we published a few papers already, and we still find this is kind of a puzzle. We sometimes it's very easy to get lost because there's so many factors, and we don't know. When you keep getting scans real surface, what is the real contact situation at different domains? What's that? There's no way we can modify or monitor that process. So there's a lot of things we still need to improve in the future. So my student is going to have another talk this afternoon on the investigation of artifact phenomena in scanning thermal microscope. So we found that the thermal mapping has certain relationship with topography, and that how the tip is going to contact with different roughness surfaces, especially comes with different curvature, and how that will change the thermal reading. Okay, I will conclude here. Thank you very much for the opportunity. I hope you enjoyed. Thank you.
Thank you, Jack. So we have room for questions. One or two. Yes.
What do you think is the radius of your probe?
100 nanometer.
How do you know?
That's from the manufacturer. We actually.
And you trust them?
I don't know, but we try to do it. So I think that's a rough number. So as long as at the same order of magnitude, as long as say 1 nanometer and 100 nanometer makes big difference. But from like 10 to 100, the difference is not that much because our model can tolerate a certain value in that range.
Yes, question.
I'm trying to understand. For this method to work, do you need your cantilever to have a much higher thermal conductivity than your sample?
Yes. Because the cantilever itself, like those thermally conductive probe, comes with metals, so those are highly thermally conductive. So we can neglect that part when we do the thermal analysis.
Okay.
Yeah.
Okay.
No.
Yes. Yes. Yeah.
So the nice thing about the scanning Kelvin probe microscope is it's a null measurement, right? You put a voltage on your tip to null the forces, and at that point, the voltage on the tip equals the surface potential.
Okay.
So what about doing these measurements, like you have a heat source below your film that's localized, and you measure the surface temperature by varying the temperature of your probe so that no heat flows?
No.
Because if you do that, then that null condition will be independent of any detail of the probe.
Ah.
Right?
So you
So
mean
if you
we can control the sample surface temperature,
Yeah.
and then we control the tip surface temperature to match the temperature, and then
Yeah.
that's a good idea.
That's why I was wondering about the conductivity.
And somehow with polymers, it should be interesting to couple it with infrared.
Oh, infrared, yeah.
Infrared. Okay, well, anyway, I'd like to thank Jack again
Thank you.
For this talk. So why don't we give him another round of applause?